A microwave network is formed when several microwave devices and components are coupled together by transmission lines or waveguides for the desired transmission of a microwave signal. For a low-frequency network, a port is a pair of terminals, whereas for a microwave network, a port is a reference plane transversed to the length of the microwave transmission line or waveguide. In a low-frequency network, the input and output variables are voltage and current, which can be related in terms of Z parameters, Y parameters, H parameters, and ABCD parameters. A two-port network can be represented by below figure. This is a port 1 and port 2. V1 and V2 are the voltage variables and I1 and I2 are the current variables. Z parameter can be represented by voltage equation. V2 is equal to Z11, Z12, Z21, Z22. I1 and I2. Similarly, Y parameter I1, I2 is determined by current equation Y11, Y12, Y21, Y22. Here V1, V2. For Z parameters, we derive the impedance matrix by selectively stimulating each port with a current source and observing voltage at all ports. Once the impedance matrix is ready, all that has to be done is to multiply it by any new current vector to give us all port voltages. Similarly, for Y parameters, we derive the admittance matrix by selectively simulating each port with a voltage source and observing current at all ports. Once the admittance matrix is ready, all that has to be done is to multiply it by any new voltage vector to give us all port currents. Each of Z and Y parameters could be frequency dependent. H parameters V1 I2 is equal to H11, H12, H21 and H22 and I1 V2. H parameters are useful in describing the input and output characteristics of the circuit. Hybrid parameters use voltage ratio and current ratios to represent the relationship between voltage and current in a two-port network. Now ABCD parameters representing by V1, I1, is equal to A minus B C minus D into V2 multiplied by V2 and I2. ABCD parameters provide the link between the supply and receiving end voltages and currents, considering the circuit elements to be linear in nature. Impedance, admittance, hybrid, and ABCD parameters can be easily measured at low frequencies under short or open circuit conditions and can be used for analyzing the circuit. At microwave frequencies, the voltage and current are difficult to measure because equipment is not available to measure the total voltage and total current at any point. Second reason, over a wide range of frequencies, short and open circuits are difficult to realize, and active devices such as power transistors, tunnel diodes, etc. will become unstable under short or open circuit conditions. At microwave frequencies, the physical length of the component or line is comparable to or much larger than the wavelength. Thus, the voltage and current are not well defined at a given point for a microwave circuit. Therefore, a new representation is needed to overcome these problems at microwave frequencies. The logical variables are traveling waves rather than voltages and currents, and these variables are labeled as scattering or S parameters. S parameters for a two-port network are represented as below figure. S parameters are usually displayed in a matrix format with the number of rows and columns equal to the number of ports. These S parameters can be represented in an equation form related to the traveling waves A1, A2 and B1, B2, where A1, A2 and B1, B2 are the traveling waves, A1, A2 are the incident waves, and B1, B2 are the reflected waves at the respective ports. Therefore, microwave circuits are analyzed using scattering or S parameters, which linearly relate the reflected waves amplitude with those of incident waves. S parameters are mostly used for networks operating at radio frequency and microwave frequencies where signal, power, and energy considerations are more easily quantified than currents and voltages. S parameters refer to the scattering matrix of a microwave network. The scattering matrix is a mathematical construct that quantifies how RF energy propagates through a multi-port network. S parameters are complex numbers having real and imaginary parts or magnitude and phase parts because both the magnitude and phase of the incident signal are changed by the network. S parameters are usually displayed in a matrix format with the number of rows and columns equal to the number of ports. For the S parameter Sij, the J subscript stands for the port that is excited and the I subscript is for the output port. Thus, S11 refers to the ratio of the amplitude of the signal that reflects from port 1 to the amplitude of the signal incident on port 1. Parameters along the diagonal of the S matrix are referred to as reflection coefficients because they only refer to what happens at a single port, while off-diagonal S parameters are referred to as transmission coefficients because They refer to what happens at one port when it is excited by a signal incident at another port. S matrices for one port, two port, three port, etc. Each S parameter is a complex number, so if actual data were presented in matrix format, a magnitude and phase angle would be presented for each Sij. S parameters describe the response of an n-port network to signal incident to any or all of the ports. The first number in the subscript refers to the responding port, while the second number refers to the incident port. Thus, S21 means the response at port 2 due to a signal at port 1. The most common N-port networks in microwaves are one-port and two-port networks. Three-port network as parameter are easy to model with software, but measurements are difficult to perform the accuracy. The signal at port 1 can be thought of as the superposition to two waves traveling in opposite directions. By convention, each port is shown as two nodes, 1 and 2, so as to give a name and value to those opposite direction waves. The variable AI represents a wave incident to port I, and the variable Bj represents a wave reflected from port J. The magnitude of the AI and Bj variables can be thought of as voltage-like variables, normalized using a specified reference impedance. This is very convenient since the square of these magnitudes are then equal to the power level of the waves. S parameters don't mean much unless we know the value of the reference impedance. We can measure S11 and S21 when ZL equal to Z0, load impedance is equal to line impedance. If we want to measure S11, we inject a signal at port 1 and measure its reflected signal, and no signal is injected into port 2. For S21, we inject a signal at port 1 and measure the resulting signal power leaving port 2. We can measure S12 and S22 when source impedance is equal to line impedance. Z is equal to Z0. To measure S12, we inject into port 2 and measure the signal power leaving port 1. For S22, we inject a signal at port 2 and measure its reflected signal. Following are the benefits of S parameters. It helps in ease of measurement at high frequencies compared to open or short current or voltage. S parameters are used to extract transmission line parameters. The return loss, insertion loss, gain, VSWR, reflection coefficients, and transmission coefficients of the network are derived using S parameters. It is easy to convert S parameters of S matrix to other parameters. If you go through the disadvantages, S parameters are useful in frequency domain analysis and not time domain analysis. Conversion between time domain and frequency domain introduces error. It's not possible to describe network in terms of both voltages and current waves using S parameters. In a reciprocal network, the impedance and the admittance matrices are symmetrical. Proof: consider multiport network. Let Vn plus is incident wave amplitude, Vn minus reflected wave amplitude. Therefore, total voltage is sum of incident wave amplitude and reflected wave amplitude is equal to 0 at all ports except ith port where fields are EI and HR. Similarly, Vn equal to 0 except jth port where fields are E and H at jth port. As per Lorentz reciprocity theorem, considering a volume containing two sets of sources, ith and jth port, which each produce fields, EIHI and EJHJ respectively. From Lorentz reciprocity theorem, where S is the closed surface area of the conducting walls enclosing the junction and N ports in the absence of any source. Since the integral over the perfectly conducting walls vanishes, the only non-zero integrals are those taken over the reference planes of the corresponding ports. So that equation 1 becomes as we know all Vn equal to 0 except Vi and Vj. Equation 2 becomes Question 3 can be read as where Pij represents the power at reference plane I due to an input voltage at plane J. From the admittance matrix representation, I equal to Y parameter into V and power relation V into I. Equation 4 becomes Vi, Vj, Yij is equal to jth port I Yji. Therefore, Yj equal to Yji and Zij equal to Zji. This proves that the impedance and admittance matrices are symmetrical for a reciprocal junction.